So as a reminder, this is Bernoulli's equation, and on each side we have initial pressure, which can often be 1 atmosphere, potential energy divided by volume, and kinetic energy divided by volume. And if your potential energy over volume increases, or your kinetic energy over volume increases, one of the other things has to decrease, because pressure plus potential energy over volume plus kinetic energy over volume always remains the same. And then units are there, but you got those yesterday. Let's now look at a mathematical, not just conceptual example of how we use this equation. But before we do that, you need to know, just kind of in words, what Bernoulli's equation is. And just in case it hasn't gotten stuck in your head from yesterday's video or today's class, Bernoulli's equation is a statement of conservation of energy. Remember, you think of pressure like energy. It has 6 terms in it, so that's P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. So all of that, and often like if the fluid stays at the same height the whole time, we just ignore the part about potential energy over volume. Often, also, things might just cancel out. So this can be an intimidating equation to look at, but often things will cancel out and it gets really simple. Here's the mathematical problem we're going to look at. If the pressure at A, this point right here, is 9.5 atmospheres, so I'm going to label this chart just because, or this diagram, because there's a lot of space on it. So right here at A, pressure equals 9.5 atmospheres. And the water's velocity is 10 meters per second, so V is 10 meters per second. What is the velocity of the water at point C? So we want to know the velocity up here. Well, we just learned an equation, Bernoulli's equation, that can take pressures and tell me a velocity. So let's see if that helps. Okay, so Bernoulli's equation says initial pressure at point 1 plus rho g, the height of point 1, plus 1/2 rho times the velocity squared at point 1 equals pressure at point 2 plus rho g, the height at point 2, plus 1/2 rho times velocity at point 2 squared. Let's see if we know everything in this equation, or know enough to find velocity before we start plugging in. So the problem says the pressure at A is 9.5 atmospheres, so we know the pressure at point 1. We know the density of water, 1,000 kilograms per meter cubed, so rho of water is 1,000 kilograms per meters cubed. No gravity on Earth. If we can define this height at point 1 to be 0, since that's a potential energy per volume, and potential energy we can call 0 wherever we want. We know the density of water, we know the velocity at point A, part A, it's 10 meters per second. We don't know the pressure at point C, so we don't know this. We do know water, gravity, height of point C. We know density of water. We don't know the velocity at point C, though. We have an equation with 2 unknowns, so we simply cannot find out either thing right now. We either have to find out the pressure some other way, or Bernoulli's equation is not what we're going to use to find out the velocity, so we might have to find that out some other way. You have learned a couple other equations for pressure, and there's one that has velocity in it. So there's an equation that can tell you the velocity of a fluid that you've learned. Think about it, look back in your notes, hopefully a question will pop up here. What other equation can tell us the velocity of a fluid? The other equation that can tell us the velocity of a fluid is the principle of continuity. Area 1 times velocity 1 equals area 2 times velocity 2. So Bernoulli's equation didn't work, I wonder if we know enough to use the principle of continuity. How will we find the area at point A? Well, the problem tells us the radius of the pipe. And the radius, since it gives us radius, implies that the pipe is a circle. So the area at point 1 would simply be pi times the radius squared. If I quickly convert 4 centimeters into meters, it's 0.04 meters squared. So looks like we could have A. We know velocity 1, that's still 10 meters per second. Do we know A2? Well, at point C, it tells us the radius. And the pipe radius at point C is also 4 centimeters, meaning that the area would also be pi times 0.04 meters squared. So wait a second. If those two areas are the same, doesn't that mean that the two velocities must be the same? So if same, then the velocity must be the same. So velocity at point 2 must be 10 meters per second. Check. The problem also wants us to find the pressure at point C. Well, now that we have the velocity right here, we know everything in Bernoulli's equation except the pressure at point C, and so we could solve for that. So let's rearrange Bernoulli's equation to find the pressure at point C. First, I'm just going to rewrite Bernoulli's equation. P1 plus rho g y1 plus 1/2 rho v1 squared equals P2 plus rho g y2 plus 1/2 rho v2 squared. Now remember I told you that lots of things in this equation tend to turn to 0 or cancel. Well, first of all, we called the level of point A 0, so this term, the potential energy part of point A, disappears. We also just found out that the velocities are the same, and this is water all throughout, so the densities would be the same as well. If these two terms are the same, and I were to subtract one of the terms from one side, I would have to subtract it from the other side, and it would simply turn to 0. So if those two terms are the same, they will cancel out. And now the equation is just P1 equals P2 plus rho g y2. So if I subtract rho g y2, I have P1 minus rho g y2 equals P2. And I can substitute in the numbers now. And I've included the answer on this slide so that we can see if I get it right. That's 800,000 newtons per meter squared, or 800,000 pascals. So the pressure at point 1 is 9.5 atmospheres. And an atmosphere is 100,000 pascals, so that would be 950,000 pascals. I just multiplied 9.5 times 100,000. Minus rho g y2, okay, rho for water is 1,000 kilograms per meter cubed. Gravity on Earth is 10 newtons per kilogram. And the height of the pipe at point 2 is 15, and I do believe those are m's, it's kind of small now, meters. And that's going to give us pressure too. So let's calculate that. This rho gy term right here, 1,000 times 10 would be 10,000, times 15 would be 150,000 pascals. So 950,000 pascals minus 150,000 pascals is 800,000 pascals. And we're good. 800,000 pascals. Big takeaways. You may sometimes have to use multiple equations to get to an answer, kind of like in kinematics, kind of like in energy. The principle of continuity is a super helpful one. It's one of those always, always, always things. A1V1 equals A2V2. That's it for this part of the video. Next, I want to show you how we can relate kinematics to pressure.